Okay, so have you ever been in that spot, where you're trying to make a decision,
Uh-huh.
but like the right way to go just isn't clear?
Yeah,
It
totally.
reminds me, I was thinking about, imagine being in Romania,
Okay.
in Arad
Mm.
specifically, and you have a flight to catch in Bucharest.
Mm,
And you're looking at a map, right, with all these roads going to like Sibiu, Timisoara, Zarand.
yeah.
It's like, where do I even start? That feeling,
Mm.
of needing to figure out the path,
Mm.
but it's not obvious.
Yeah, I get it.
And this is something, well, computers actually face this all the time,
Right.
except they have these really powerful tools to sort it out.
Yeah, they do. I mean, it's actually pretty amazing what they can do now. What's so interesting about this is that this very human problem, how do we get from point A to point B when the way isn't clear? Well, in the AI world, we call that search. So when we talk about a problem-solving agent, we're basically describing a computer system that can plan ahead. It can explore different sequences of actions, different paths, really to figure out how to reach a specific goal. It's like a super smart shortcut for decision making, especially in situations where things are complex.
Okay, that's fascinating. So we're talking about computers literally searching for solutions, just like we might search for a path on a map.
Exactly. And that's precisely what we're diving into today. How do computers solve these what should I do next puzzles, particularly when the answer isn't immediately obvious? We're going to use some of the brilliant insights from the work of Stuart Russell and Peter Norvig, who are, true pioneers in AI, to really unpack the fundamental principles of this whole search process. Our goal today is to give you a clear understanding of how computers find solutions when the answer isn't just staring them in the face.
Awesome. I'm excited to dig into this.
Me too. And to give you a sense of scale, think about this. These search methods aren't just about navigating a map. The same core ideas apply to incredibly complex problems. For example, VLSI layout. That's the design of those super intricate layouts for components on a microchip.
Oh, wow. Yeah.
Or even figuring out how proteins fold, which is critical for developing new medicines. This search concept is really powerful and touches so many different fields.
So it seems like there are different levels of smartness to these search methods.
Definitely.
Earlier, you mentioned uninformed and informed search.
Uh-huh.
What's the big difference there? And how does a computer even get started tackling these problems?
Great questions. So, for a problem-solving agent, there are four key phases. First, we have goal formulation, which is pretty much like it sounds. It's about the agent figuring out exactly what it wants to achieve.
Okay.
In our Romania example, the goal is getting to Bucharest.
Makes sense.
Then comes problem formulation. This is about identifying all the relevant states, like the different cities and the actions, like the roads connecting them, needed to move towards the goal.
Okay.
Then comes, of course, the actual search itself, where the agent explores potential sequences of actions to figure out a path to the goal.
Got it. And then the last step.
The final step is execution, where the agent actually carries out the plan it's come up with.
Okay, so let's break this down a bit more. Going back to our Romania road trip, the goal is Bucharest.
Right.
What would problem formulation actually involve?
Okay, so let's keep it simple. The states are the cities. The initial state is Ered, that's where we start. The goal state is Bucharest, our destination. The actions available to us from any state are the roads leading out from that city.
I'm following so far.
So from Arad, our actions are things like drive to Sibiu, drive to Timisoara, or drive to Zarand. Now, the transition model describes what happens when we take an action. If we take the action drive to Zarand from Arad, the result is that we're in Zarand.
So it describes how we change our situation by taking an action.
Exactly. Then we have the action cost function. In this example, it would be the distance in miles between the cities, which we can get from the map.
Makes sense.
So every action has a kind of price tag attached to it.
All right, so we've got the locations, the starting point, the destination, the possible ways to move between them, and how much each move costs. Cool. Now, you mentioned path and solution before. How do those fit into all of this?
Well, a path is just a sequence of actions that takes us from one state to another.
Okay.
Think of it like a list of the cities you pass through on your trip.
Right, right.
A solution, then, is a path that starts at the initial state, Arad in this case, and ends at a goal state, Bucharest. It's the complete route.
Okay.
And of course, the best solution, the one we're usually after, is the optimal solution. This is the solution with the lowest total path, costs the shortest total driving distance.
So the shortest route, not just the one with the fewest stops.
Exactly. And earlier I mentioned something about a graph.
Yeah, you did.
This whole state space, meaning all the possible situations our agent could be in, can be visualized as a graph. The cities are the vertices, or nodes, in the graph, and the roads connecting them are the edges.
It's like a network of possibilities.
Right. Our Romania map is a perfect example of this kind of graph.
Okay, that's a good way to think about it.
Mm-hmm.
But the real world, obviously, is a lot messier than a simple map with a few cities.
Yeah.
How do computers handle all the extra stuff, all that complexity?
That's a great point, and it's where abstraction becomes crucial. When we're formulating a problem for a computer to solve, what we're doing is creating a simplified model of the real world.
Okay.
We intentionally leave out details that aren't essential for finding a solution. Think back to our Romania trip. What kind of music is playing on the radio, the color of the cars passing by, the exact time of day.
Right.
All of that stuff is part of the real-world situation.
Yeah.
But it doesn't fundamentally change the problem of finding a route to Bucharest.
I see.
The key is to find that sweet spot, the right level of detail. If we made our actions super granular, like turn the steering wheel 1 degree to the left,
Right.
our computer would never even get out of AROD.
So how do we figure out what level of detail is enough to make the problem solvable, but not so simplified that it's useless?
So a good abstraction, it needs to be valid. That means any solution we find in our simplified model has to be translatable back into a real-world solution.
Okay.
And it needs to be useful, meaning the actions we've defined are actually easier to carry out in the real world than the original super detailed problem.
Yeah.
Drive from Arad to Sibiu, that's a useful abstract action for a human driver.
That makes a lot of sense. So we've got the problem laid out in a way a computer can understand.
Right.
How does it actually start searching for a solution? You talked about uninformed search.
Uh-huh.
What's that all about?
Uninformed search algorithms, well, they're exactly what they sound like. They don't have any special knowledge or insights about how close a state is to the goal state. Imagine our agent in Arad, but with zero knowledge of Romanian geography.
Okay.
It wouldn't have any idea if heading towards Zărand or Sibiu is a better first move towards Bucharest.
Got it.
It's like navigating a maze in complete darkness. You just try different paths, hoping for the best.
So what are some of the basic uninformed search strategies?
Well, one of the most straightforward is breadth-first search.
Okay.
Picture this. You explore the possibilities level by level.
Okay.
You start at Arad, then you explore all the cities directly connected to Arad, Sibiu, Timisoara, Zărand, and then you explore all the cities connected to those, and so on. It's like this expanding wave of exploration that spreads outward from the starting point.
So it's systematic.
Yeah, exactly. Now, breadth-first search has a big plus.
Right.
This is complete, meaning if there's a solution out there, it'll find it, even if the problem space is huge, even infinite, theoretically.
That's good.
And if all actions cost the same, like every step is just one move, it's optimal. It'll find the solution with the fewest steps. The way it works is using a FIFO queue, first in, first out. That ensures we explore all the options at one level before going deeper, but there's a catch.
Okay, what's the catch?
It's complexity. The time it takes to find the solution and the amount of memory it needs, they can both increase exponentially as the solution gets deeper. For example, let's say you have 10 possible actions from each state, and the solution is 10 steps deep.
All right.
You're talking about potentially exploring and storing an astronomical number of possibilities. It could require terabytes of memory, which is a major limitation.
Wow, that's a ton of memory.
So breadth-first search. Guaranteed shortest path in terms of steps, at least, but at a potentially massive memory cost.
So are there other uninformed approaches that try to be a bit more efficient?
Yes, absolutely. Another important one is called uniform cost search. It's also sometimes called Dijkstra's algorithm. This one's particularly handy when the cost of different actions varies, like those distances between cities on our Romania map. It doesn't just blindly explore level by level. It prioritizes exploring the path with the lowest total cost discovered so far.
Okay.
It's like always going for the cheapest option at each step.
Got it.
To do this, it uses a priority queue. That's a data structure that keeps tabs on all the possible paths and always picks the one with the lowest accumulated cost to explore next.
Smart.
So uniform cost search is also complete. And it's cost optimal, meaning it finds the solution with the absolute lowest total cost.
That sounds like the best of both worlds.
Yeah, but even uniform cost search can get pretty computationally expensive. Its time and space complexity can sometimes be even higher than breadth-first search, especially if there are many low-cost paths that lead to dead ends.
So it can get sidetracked.
Yeah. It's like exploring a bunch of slightly cheaper, tempting wrong turns before stumbling upon the truly optimal path, which might have initially seemed a bit pricier.
I can see how that would happen. Okay, so we've got breadth first and uniform cost, which both explore pretty broadly.
Uh-huh.
What about an approach that goes deep instead of wide? Would that be depth first search?
Exactly. Depth-first search dives deep down one path as far as it can go before backtracking and trying another path.
Okay.
It explores one branch of the search tree until it hits a dead end or the goal, and then it backtracks and tries a different branch.
Got it.
Now, one major advantage of depth-first search is that it's very light on memory usage, especially if you implement it without remembering all the states it's already visited.
Okay, so that's a plus.
It only needs to remember the current path it's exploring.
That makes sense. But wouldn't going deep like that be risky?
Hmm.
What if it gets stuck on a path that's infinitely long and never reaches the goal?
That's a valid point. And
Ah.
that's actually one of the biggest limitations of depth-first search. It's not complete in infinite or cyclic state spaces. It could just keep going down one rabbit hole forever without finding a solution.
Oh, no.
And even if it does find a solution, it's not guaranteed to be the optimal one. It stops as soon as it finds any solution, which might not be the best one.
That makes sense.
Now, to deal with these potentially infinite paths, there's depth-limited search, where we set a maximum depth for the search.
Okay.
But then, the tricky part is figuring out the right depth limit.
Right. Too shallow and you might miss the solution.
Exactly. And too deep, you run into the same problems as the regular depth-first search.
So how do you pick the right depth?
Well, there's a really clever approach called iterative deepening search. It kind of combines the best of both worlds, depth-first and breadth-first search.
Okay.
What it does is it starts by performing a depth-limited search with a limit of 0.
Okay.
If it doesn't find a solution, it bumps the limit up to 1 and tries again. Then 2, and so on. For each depth limit, it does a complete depth-first search. This way, we get the memory efficiency of depth-first search while also achieving the completeness and optimality for uniform action costs, at least of breadth-first search.
So it's like a repeated, more intelligent depth-first search.
Right. And the amazing part is that its total time complexity is often comparable to breadth-first search, even though it seems like it's doing a lot of redundant work.
That's pretty cool how we can get the best of both worlds. Is there any other big uninformed search strategy we should know about?
Yeah, let's talk about bidirectional search.
Okay.
The idea here is to search forward from the initial state that's Arad at the same time you're searching backward from the goal state that's Bucharest, hoping they'll meet somewhere in the middle.
Like two teams digging a tunnel from opposite ends.
Exactly. It makes sense, right? Searching halfway from both ends is much faster than searching all the way from one end.
Yeah, that's a great analogy.
For example, imagine the solution is deed steps away. Unidirectional search, it might explore something like b to the power of deed states, where b is the branching factor, how many choices we have at each step.
Right.
But a bidirectional search could explore maybe 2 times b to the power of d2. That could be a huge time saver.
Right, a much smaller number.
Now, to make bidirectional search work smoothly, you have to be able to reason backward from the goal. So like, what actions could have led to this state?
Okay.
And you need a good way to know when those two search frontiers have met.
Right, yeah, like a signal flare.
Right. There are different strategies for this, like bidirectional best first search.
Cool.
And when it's done right, bidirectional search can give a big boost to performance.
Okay, so we've got a good handle on uninformed search methods. It sounds like they're the standard tools when you're going in blind with no clues about where the goal might be.
Right.
But what happens when you do have some hints about where to look? I think that's where informed or heuristic search comes in, right?
You got it. Informed search strategies are all about using what we call heuristic functions. These heuristics estimate the cost of the cheapest path from a given state to the goal state. Think of them like providing the search algorithm with some domain knowledge, some educated guesses, to help it prioritize the paths that are more likely to lead to the solution quickly.
So giving the computer a little bit of insider information.
Exactly. It's about leveraging knowledge to make the search more efficient.
Okay, so in our Romania problem, what would be an example of a heuristic?
A good one for that scenario is the straight line distance between any city and Bucharest. It's not the actual road distance, of course,
Right.
but it gives us a reasonable estimate of how far away the goal is as the crow flies, so to speak.
That's helpful.
It's a piece of information our agent can use to guide its search.
Okay, so how do we actually use these heuristics in search algorithms?
One of the most simple ways is with what's called greedy best first search. This algorithm just picks the node that looks closest to the goal, the one with the lowest heuristic value, and expands that.
Right.
It's like always going for the most tempting, closest looking option.
Got it.
Yeah.
But is that always the best strategy? Couldn't it lead to problems?
It can. A greedy best first search, while it might find a solution really quickly, is sometimes too short-sighted. It focuses so much on the immediate estimated cost to the goal that it can overlook a path that looks a little less promising at first, but actually turns out to be the overall best solution in the long run.
So we can get tricked by appearances.
Yeah. It's greedy in that it prioritizes short-term gains over the best overall solution. It is complete in finite state spaces, meaning it will find a solution if one exists,
Okay.
but not in infinite ones. And its efficiency really hinges on how good the heuristic is.
Right. So it can be fast, but not always the smartest.
What's a more robust, informed search method?
A search is probably the most well-known and often the most effective informed search algorithm.
Yeah, pronounced A star. A combines two costs. The cost of the path from the start to the current node, which we call the G cost, and the estimated cost from the current node to the goal, which is our heuristic, the H cost. It adds those two together to get an overall evaluation function for each node, which is called F. F of n equals G of n plus H of n. Essentially, F of n gives us an estimate of the total cost of the best path that goes through that node n.
So it's not just about how close we are to the goal, but also how much it costs to get where we are.
Exactly. It considers both the path traveled so far and the estimated cost to the goal. A search always expands the node with the lowest F value. Now, a really important concept here is what we call an admissible heuristic.
Okay.
An admissible heuristic never overestimates the actual cost to reach the goal from any given state. It's always optimistic, never exaggerating.
Okay.
If our heuristic is admissible, then a search has some really powerful guarantees. It's complete, meaning it will find a solution if one exists, and it's cost optimal, meaning it will find the solution with the lowest total cost.
That sounds great.
Mm-hmm.
How does the admissibility of the heuristic guarantee that the solution will be optimal?
It's based on this idea that A will never choose a suboptimal goal node to expand. If it did, it means there's another node on the frontier, a node we found but haven't explored its neighbors yet, which is on the optimal path and has an F value less than or equal to the cost of the optimal solution. Because our heuristic is admissible, its A value won't be an overestimate, so its F value will be a realistic lower bound on the total cost through that node. Now, another related concept is what we call a consistent heuristic.
Yeah.
A consistent heuristic is one where the estimated cost from a node to the goal is never greater than the cost of taking one step to a neighbor plus the estimated cost from that neighbor to the goal.
Got it.
A consistent heuristic is always admissible and has a nice property. A doesn't need to reopen nodes it's already explored, which can save time.
That makes sense. You also mentioned something about visualizing search with contours. What did you mean by that?
Okay, so imagine drawing lines on our Romania map. For a search, a contour would connect all the cities that have the same F value, the same G plus H.
Okay.
A search basically expands outwards in these bands of increasing F costs. When you've got a good informative heuristic, these contours sort of stretch towards the goal, making the search really focused.
I see.
Now, compare that with uniform cost search. Remember, uniform cost only considers the G cost, so it expands more like concentric circles around the starting point, exploring in all directions equally based on the cost incurred so far.
So it's a less focused search.
Yeah, exactly. A search is much more directed, which makes it more efficient overall. It cuts out large portions of the search space that are unlikely to have the optimal solution. It doesn't waste time exploring dead ends.
That makes sense. But didn't you also hint that a search might have its own challenges?
It does. The main challenge with a search in practice is its memory usage. In the worst case scenario, the number of nodes it has to keep track of can still grow exponentially with the depth of the solution, especially for really large problems. It's possible for A to simply run out of memory before it finds the answer.
So we're back to memory limitations, just like with some of those uninformed searches.
Mm-hmm.
What are some strategies for dealing with that when memory is a big bottleneck?
Well, there are some clever tricks to save memory. One way is to be really efficient in how you actually store the state information.
Okay.
But more importantly, there are special memory-bounded search algorithms designed to deal with this issue head-on.
Got it.
One approach is called beam search. In beam search, what you do is limit the number of nodes you keep on the frontier, the nodes you're actively considering, to just the gay best ones, according to your heuristic.
Okay.
This way, you use much less memory. But there's a trade-off. You might miss the absolute best solution, or even any solution, if the optimal path happens to go through a node that was pruned away.
So it's about finding a good enough solution that fits in memory, rather than guaranteeing you get the absolute best one.
Exactly. It's a balance between speed, memory, and optimality. Another very important memory-bounded algorithm is iterative deepening A, IDA. It's basically the memory-efficient version of A search.
Okay.
It works similarly to iterative deepening we talked about for uninformed search, but instead of using a fixed depth limit, it uses the F cost, that's G plus H, as the cutoff. So in each iteration, it does a depth-first search, but only explores nodes whose F cost is below the current threshold. If it doesn't find a solution, it increases the threshold to the minimum F cost of any node it pruned in the previous iteration.
So it's being more selective.
Yeah. This approach manages to achieve the optimality of A search, assuming the heuristic is admissible, while using the linear memory of depth-first search. It's really useful for problems where the solution is deep, and regular A search would eat up all the memory.
So IDA sounds super practical for those really big problems. Are there other memory-saving techniques we should know about?
There's also recursive best first search, RBFS. RBFS tries to mimic A search, but using only linear space complexity. It's a recursive algorithm that keeps track of the F value of the best alternative path available.
Yeah.
If the F value of the path it's currently exploring goes above the F value of that best alternative, it backtracks and explores that alternative instead. Now, while it uses less memory than A, RBFS can sometimes end up exploring the same parts of the search space multiple times, which can slow it down.
So it's like going back and forth, second-guessing itself a bit.
Right. And then there's SMA, Simplified Memory Bounded A. SMA is designed to make the most of whatever memory it has available. It expands the node with the lowest F value until the memory is full. When it needs to add a new node and there's no memory left, it drops the worst leaf node, the one with the highest F value, and stores its F value in its parent.
Interesting.
This way, it can backtrack later and explore that path again if needed.
That's clever.
Now, SMA is complete, meaning it will find a solution if one exists and can fit in memory, and if an optimal solution can fit in memory. It's a good general-purpose algorithm for cases where you have a strict memory limit.
So it's like making the best of a tight situation. We talked about bidirectional search before in the context of uninformed methods.
Yeah.
How do heuristics play into bidirectional search?
So when you try to combine heuristics with bidirectional search, we call it bidirectional heuristic search, and things get a little more tricky.
Okay.
Simply using f of n equals g of n plus h of n in both directions doesn't automatically mean you'll get the optimal solution or even get the speed boost you might expect. You have to be more strategic about how you define and use those heuristics in both the forward and backward searches.
Right.
And you also have to think about how you decide when the two searches have truly met in a meaningful way.
Okay, that makes sense.
For instance, you might have a forward heuristic that estimates the cost to the goal and a backward heuristic that estimates the cost from the goal to the current state. And there are more sophisticated evaluation functions designed to help the two searches meet effectively in the middle while guaranteeing you'll find the optimal solution. The key is to ensure those heuristics work in harmony to guide the search in the right direction.
Okay, I'm starting to see how the power of informed search really depends on the quality of the heuristic you choose.
Yeah.
So where do these crucial heuristics come from?
That's a fantastic question. The performance of any informed search algorithm is directly tied to how well the heuristic function estimates the true cost to the goal. For example, consider the classic 8 puzzle problem. That's where you have a 3x3 grid with numbered tiles and a blank space.
Yeah, I've seen that.
The goal is to arrange those tiles in a specific order.
Got it.
Now, two common admissible heuristics for the 8 puzzle are H1, which is just the number of misplaced tiles,
Okay.
and H2, which is the Manhattan distance. The Manhattan distance is the sum of the horizontal and vertical distances of each tile from where it should be. Generally speaking, the Manhattan distance, H2, is a better heuristic than the number of misplaced tiles, H1, because it gives a more accurate idea of how much work is left to do.
So it's a better measure of progress.
Right. If a tile is way off from its correct position, the Manhattan distance will reflect that much more strongly than simply counting it as one misplaced tile.
That's a good point. How do we actually compare the effectiveness of different heuristics?
One way is to look at what's called the effective branching factor. Imagine our search generates a total of n nodes to find a solution at a depth of d.
Okay.
The effective branching factor, which we denote as b, it's the branching factor that a uniform tree of depth would need to have in order to contain n nodes.
Okay.
A good heuristic is one that gives us a lower effective branching factor because it means our search is more focused and explores fewer useless nodes.
Right. Less wasted effort.
Another way to think about it is how much the heuristic effectively reduces the depth of the search compared to an uninformed search.
Makes sense. Now, you also mentioned something about generating heuristics from relaxed problems. What's that all about?
The idea with relaxed problems is that you take your original problem and simplify it by removing some of the restrictions on the actions.
No.
And here's the key. The cost of the optimal solution to this simplified, relaxed problem is always an admissible heuristic for the original, more restricted problem.
Why is that?
Well, because any solution to the original problem is also a solution to the relaxed problem. It still meets the fewer restrictions, right?
Right.
And its cost will be at least as high as the optimal cost in the relaxed version.
Okay, that makes sense.
Let's go back to the 8 puzzle. We can relax the rule that a tile can only move into the adjacent blank space. If we let tiles move anywhere on the grid, well then the number of misplaced tiles, H1, becomes the exact cost to solve that relaxed problem. Each misplaced tile just needs one move. If we relax things a bit less and say a tile can move to any adjacent square, even if it's occupied, then the Manhattan distance, H2, becomes the optimal cost for that relaxed scenario. The key is that these relaxed problems should be easy to solve, without needing a ton of search themselves. We can also combine different admissible heuristics. Just take the maximum of their values that's still admissible and at least as good as any of the individual ones.
That's a clever technique.
Oh.
What other methods are there for coming up with good heuristics?
Another really powerful technique involves using subproblems. What you do is pre-calculate the exact cost of solving smaller chunks of the overall problem and store those solutions. For instance, with the 8 puzzle, we could focus on getting just a few specific tiles into their correct spots without worrying about the other tiles. We could calculate the best possible way to do that for every possible arrangement of those few tiles and the blank space.
Okay.
We would store all those costs in what we call a pattern database.
Fine.
Now, during our main search, whenever we encounter a state of the 8 puzzle, we can quickly look up the cost of solving that little subproblem in our pattern database.
That's pretty efficient.
And that cost gives us an admissible heuristic because the cost of solving that smaller part of the problem can never be more than the cost of solving the whole thing. We could even use multiple pattern databases, each focusing on different sets of tiles. And there's a really cool technique called using disjoint pattern databases, where the subproblems don't overlap in terms of the moves required to solve them. In those cases, you can add the heuristic values from the different databases together, and that gives you a super powerful, accurate, admissible heuristic.
So it's about strategically breaking down the problem into manageable chunks. What about real-world situations like, say, online driving direction services? How do they figure out the best routes so quickly?
They rely heavily on pre-computation. One key technique is choosing important landmark points on the map, maybe major cities or key intersections. They then pre-calculate the optimal path costs between all pairs of landmarks and from every point on the map to all the landmarks.
Interesting. And then during a route query.
Exactly. When someone asks for directions, they can use those pre-computed distances to quickly estimate the cost to the destination. A simple heuristic, though not always admissible, could be to look at a bunch of landmarks, and for both your current location and your destination, estimate the cost as the lowest sum of cost to landmark plus pre-computed cost from landmark to goal. More advanced methods, like the differential heuristic, which looks at the difference in optimal costs to and from landmarks, can be admissible and